This is starts chapter 7. It says, as long as chemistry is studied, there will be a periodic table. And even if someday we communicate with another part of the universe, we can be sure that one thing both cultures will have in common is an ordered system of elements that will be instantly recognizable by both intelligent life forms. So there is some thought that the idea that we could compare our periodic table with possibly another civilization's is one of the hallmarks of being able to have a common thing that we could communicate with. So this is chapter 7, and we want to be able to calculate the effective nuclear charge for atoms and ions, use the atomic model to explain periodic trends, including but not limited to atom size, electron affinity, and ionization energy. The first thing you have here is Mendeleev's periodic table. This was the first attempt to organize the elements by properties, and Mendeleev himself organized them by mass. He saw a similarity whenever chemical properties lined up according to mass, and he left gaps to predict future elements. So this is the first real attempt to organize the elements in any sort of systematic way. And it actually was a very good job, but it turns out that it's not the best way. In 1913, Thomson found evidence for isotopes. And what he did was an extension of the Thomson experiment, different Thomson. But what they did is they fired atoms between charged plates. And whenever they fired atoms between charged plates, you expect them to curve along a certain path. So all of carbon dioxide goes one way, all of carbon monoxide goes one way. But the interesting thing about this was when they did it for neon, there were two distinct lines. There was one that was here, and there was one that was here. And so the question is, why were there two distinct lines? And the evidence was, well, the only way that this would happen is they were exposed to the same charge, they were fired with the same velocity. The only explanation would be that maybe the neon has different mass. And so that was the evidence that they had that isotopes were the case. So here's the problem. You have an element of neon that has a very, very specific reactivity, and now it has different mass. So we come up with Mosley's periodic table. Mosley's periodic table, organized by atomic number, which is the number of protons. It's more consistent as far as lining up chemical reactivity than it was with atomic mass, so it's better in that respect as well. And then the vertical columns have similar chemical properties. It is important that you bookmark ptable.com. It is a quick reference for you to be able to say, okay, this is what I need to know about this element. This is the atomic mass of this element. This is the charge of this element. This is the electronegativity of this element. So it's a great tool for you to have. So whenever we look at the periodic table in the atom, we look at the proton and electron interaction. And atoms tend to be held together by the electrostatic force. That's the attraction between the positive protons and the negative electrons. Like we said, opposites attract. You have a positive charge and a negative charge, and they attract to one another, and that's what holds the atoms together. On kind of a side note, it's actually something called the strong nuclear force that actually holds the nucleus together. That's what keeps the positive charges together. It's actually stronger than the electrostatic force, but it acts over a very short distance. But it's this proton-electron interaction that keeps the atom together. And it does so by Coulombs Law. Coulombs Law we've talked about in first year chemistry quite a bit. It's also referenced quite a bit in physics, but it is basically the idea that the electric force is equal to a constant times the two charges divided by the distance squared. And you see those right here. You see the electrostatic force is measured in newtons. You see the constant, you see the charge, and you see the distance. Now, you're not going to be expected to do a large amount of calculations using Coulomb's law. But we're going to go ahead and start off and expect you to do some because understanding the conceptual part of Coulomb's law is really key to understanding chemical properties. So, it says determine the attractive force between a proton and an electron at Bohr's radius, which is 5.29 times 10 to the minus 11th. So we want to use Coulomb's law in order to accomplish this. So when we do that, hold on just 1 second. I'm trying to pull up a calculator. We know that the equation is F is equal to K Q1 Q2 over D squared. Now we've actually talked about this, and you can look it up on a periodic table what the charge of a proton and an electron are. The charge of a proton is 1.6 times 10 to the minus 19th, which makes the charge of an electron 1.6 times 10 to the minus 19th, but negative. So they have the same magnitude, they just have different charges. So the K value, if you were to look on the previous page, tells you that that is 8.99 times 10 to the 19th. multiplied by 1.6 times 10 to the minus 19th multiplied by negative 1.6 times 10 to the minus 19th. And you may have concerns at this point. You say, well, wait a second, that means I'm going to have a negative force. Those of you who are familiar with Coulombs law know that when you have a negative force, it simply means that it's attractive. Okay, if you have a positive force, it actually means it's repulsive, but we're not going to have that between a proton and an electron. Okay, then we would divide this by the radius, which is 5.29 times 10 to the minus 11th squared. So we plug it into our calculator, 8.99, and then you'd use your E button, 9, times 1.6, E negative 19, and then enter, and do it again, and then divide by 5.29, E minus 11, and when you do that, you got to do that twice, and you end up with a fairly small value. Okay, you end up with something like, hold on a second, something like this is 10 to the 9th, 2.72 times 10 to the minus 29th newtons. Okay, next it said, how would it be difficult to calculate the net force between protons and electrons in helium? This is a conceptual question, and the reason why is, here's my positive charge. So we're going to kind of neglect the fact that there are two positive charges and just treat it as one. So you have 2Q, and it's positive. The problem now is that you have Q, which is negative, and Q, which is negative. So you would have to take into account the attraction here, the attraction here, and the repulsion here, and the repulsion there. So it starts to be very difficult mathematically, even for something as simple as helium. Now take into account the fact that these charges right here move relative to this, and the calculation gets extremely difficult. So that's why one of the reasons why the Bohr model, or the classical model of the atom, Bohr is based on this idea of Coulomb's law, fails once you get past the past one electron. Now, we have something that's called effective nuclear charge. Coulomb's law, we just showed you, is tough for helium. Imagine trying to do it for uranium. Okay, this electron is attracted, but then it's repulsed by this one, and then it's repulsed by this one, and it's repulsed by all the other 91 electrons other than itself. So Coulomb's law can be extremely difficult. There's no way that you could get a reasonable approximation for the force of an electron and a proton on each other for a 92 electron atom. You just couldn't do it. So instead what we do is we talk about something called the effective nuclear charge. The effective nuclear charge allows us to estimate the average attractive force. So it's real key that you understand that it's an estimate, but it is a very, very, very good estimate, and it actually helps us explain all of the patterns that we see in terms of the periodic table. So it's a very good estimate, but it is by no means exact. And then it's an average attractive force. This electron will move closer to the proton, and it will be further away. So it's just taking the estimate of a snapshot and kind of putting it all together. Now, to calculate the effective nuclear charge, you use this formula. This formula is very, very simple. Z effective, that stands for the effective nuclear charge, is equal to the atomic number. This is the number of protons, and then we subtract the number of what we call shielding electrons. Another way of shielding electrons is if you think of inner electrons. Okay, so we've talked about valence electrons before. Remember, valence electrons are the ones that are on the outermost level. So if I've got two electrons here, this right here is a valence electron because it's in the outermost level. These two electrons right here would be considered to be inner electrons. Okay, so that's how we calculate the effective nuclear charge. You just take the number of protons and you subtract the number of inner electrons. So it says calculate the effective nuclear charge of bromine. So to calculate the effective nuclear charge of bromine, we're going to use the equation. Hold on just one second. Z effective is equal to Z minus S. And so we have bromine. Bromine, if you look at the periodic table, has an atomic number of 35, which means it has 35 inner protons. 35 protons. Now we have to subtract the number of shielding electrons. Now the number of shielding electrons can easily be calculated on the periodic table if you just look at it. Okay, So you find bromine's position on the periodic table, and it's roughly right here. It's a halogen, and it's in the fourth period. So now what you need to do is, in order to figure out the number of shielding electrons, you go backwards until you get to a noble gas. So the noble gas that I would get related to bromine would be argon. Okay, it's not krypton. Even though krypton's right next to it, you have to go left. So if you were to look at argon, argon has 18 electrons. So whenever you have a complete orbital shell, like in a noble gas, that references the number of shielding electrons. So if you were to draw bromine, what you would have is you'd have 2 electrons, 8 electrons, 18 electron, a total of 18 electrons. Once you got to that point right here, now we're talking about these electrons are we're talking about. That's what we're trying to find the effective nuclear charge for. The valence electrons. What's the effective nuclear charge? Because although I have an electron right here and it's attracted to this nucleus, all these other electrons are in the way. And so those electrons could repel or be on the other side and repel. And so it's taking the average of that. So the effective nuclear charge for bromine in this case would be 17. Electron shielding. So the valence electrons do not experience the full attraction of the nucleus. So that's the whole idea, that this electron right here does not experience the same 12Q positive charge because it's got 1, 2, 3, 4, 5 electrons that are kind of in the way. So that's the reason why we have this effective nuclear charge instead of just calculating the charge of the nucleus itself. There are definite trends for the effective nuclear charge. Okay, if you were to look here, this is a bar graph that represents the atomic number and the effective nuclear charge. So if you look, the atomic number increases by 1 each time because we're going up the periodic table. So you see this steady trend. And you start to see an increase there, but then it drops off all of a sudden. Okay, so all of a sudden the effective nuclear charge increases and then it drops. It increases, 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 it drops. It increase, 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 and then you could probably guess what it's going to do next. And the answer is, each time it gets to a noble gas, the very next element drops significantly. Okay, so if you were to look, the effective nuclear charge that we have for hydrogen is there are no shielding electrons, so it's 1. For helium, there are no shielding electrons, so it's 2. Once we get to lithium, the atomic number is 3, but now I have 2 shielding electrons, so it gets to be 1. I have beryllium is 4, but there are still only 2 shielding electrons. There's only 2 shielding electrons all the way until I get past neon. Once I get past neon, there are now 10 inner shielding electrons. So we have periodic trends. So the effective nuclear charge increases from left to right and increases from top to bottom. So this is a key AP idea. The properties of atoms can generally be explained by the combination of effective nuclear charge and Coulombs Law. So we're going to say, remember to clench. That's your key AP idea. If I had to say, if there's 5 ideas that you have to know going into the AP exam, this is number 1. Because it's going to explain a lot of the things that you see later. The idea of what's the effective nuclear charge, opposites attract, likes repel. This can be one of the things that makes or breaks you on the AP exam. So you need to make sure that you understand the idea of effective nuclear charge and how it relates to Coulomb's law.